So first of all, good evening, everyone. Welcome to this Big-O presentation. So people who are attending technical interviews those are preparing for technical interviews obviously would have heard about this Big-O notation. So what is Big-O notation? So today we are just going to talk about the basic concepts of how we are going to represent this complexities, time complexities and space complexities in terms of Big-O. So, given a problem, each and every one of us can come up with a solution. The solution that I give will be different from the solution that you give. So, which solution is going to be efficient? So, complexity analysis comes into picture during this scenario. Like a solution that I give might be very much time efficient in the sense it may run in 2 seconds, and the solution that you give can run in 1 second, and so on. So in this scenario, we will have to understand two concepts: understanding the complexity, that is time complexity and the space complexity. Both these complexities can be represented using Big-O. Apart from this, there is omega, theta representations and all. But in terms of the worst case scenarios, we'll be representing only using Big-O notations. So every uh, every code or every line in a algorithm uh, consumes some time and consumes some memory in space, right? So according to that, we will have to determine how much time it is going to run and how much space it is going to occupy in memory. So why are we doing this? Basically, for example, if you take an array of 5 elements and you're going to find out a particular element, in that case, you'll have to run through each and every element. You can run through each and every element in that array of 5 elements and search if an element is present or not. So this will run for 5 times, right? Because there are 5 elements and we will have to check the worst case scenario. Suppose if the element that we are searching is the first element, then the loop will come out after the first iteration itself. But what happens if the number is present at the end of the array? It's going to run for five loops, right? 5 times, 5 iterations. So this is like I'm numbering it. But what happens if there are 10 elements? What happens if there are 100 elements? Something. What happens if there are n number of elements? So we will have to represent time and the space that our code takes in terms of something, right? That notation is Big-O. So how far our code is going to be will be scalable in terms of time and in terms of memory usage. Okay. Now I'm going to go through some common time complexity and space complexity notations. And at the end, if you have any questions, you can ask. So first of all is a constant time solution. We'll go from the lower, like this is the efficient one, from the efficient one to the least efficient one. The constant time complexity is the one, it's a very efficient solution. It is represented in terms of O of 1. Okay, so it is like simple, like whenever we are declaring some variable, or whenever we are initializing some variable, or whenever we are trying to access something, do some operations within a for loop or while loop, that specific operation has a constant time. See here in the code snippet, you can see a while loop, but it doesn't mean that it's going to run for n number of times. Suppose if the user is asked for a number that is I, and the user is going to enter I as 1. So if it is going to, if one, it's going to check if 1 is less than 11, right? So this while loop will be constantly checking if it is going to be less than 11 or not. So whatever be the input, it is going to take a constant time. It's not going to, it doesn't depend on the number of input that we give. So Big-O notation is basically determined by the number of inputs that you're going to give. So whatever be the input, whatever be the size of the input, your time complexity, it's just going to be a constant factor. There is not going to be any change. Like if there are 1,000 inputs given, it's not going to increase. The time is not going to increase as such. It's just going to take a constant time for that. So you can see the graph. That's how it is represented. So O of 1 is just a horizontal line. So other examples are whenever we are doing some comparing or swapping of elements in an array, or whenever we are doing some conditional branching, everything comes under constant time complexity. So in case if we are seeing some, we are seeing a loop, for loop or while loop as in the code snippet, it doesn't mean that it is going to take like O of n times, because in such kind of scenarios, the while loop is just a comparison. It's going to run for constant time. Next will be linear time. For this, the representation is O of n. So n is the number of elements in the given input, that is the data. Uh, for this, I can give example as whenever you're trying to find an element in an array, as I told earlier, you can do a for loop, iterating each and every element, checking if the particular element is present or not. So the worst case scenario, it has to go through all the elements in the loop and then check and give us the result if a particular element is present or not, or printing all the elements. These are just common, simple examples of linear time complexity. So anything, a for loop, which is running for n number of times, n, where n is the size of the given array, then it falls under this linear time complexity, and we can represent it as O of n. So here you can see the graph. As the amount of data increases, as the input size increases, the time taken by the given algorithm, the runtime complexity, is going to increase proportionally. So here, so it's linear and it is represented by O of n. Here is another example. Like these are okay. The operation is going to merge. We are going to merge two sorted lists. So you'll have to note that it is already sorted, but we are just going to merge this two sorted list. In such a scenario, we'll be just, as the code snippet shows, like we'll be doing a while loop, uh, pointing to two arrays, having two pointers, and then checking each and every element of the two arrays and comparing it, which is greater, and we can populate another array. This snippet, just a while loop, represents O of n. So since the array is already sorted, we don't have to compare. We don't have to do internal comparison. It's merging of two sorted arrays. It's going to take O of n. Next is O of n squared, that is quadratic time. So as you can see, the curve pattern in the graph, the curve pattern like it changes. Like for constant time, it was just a horizontal line. Then it became a slope. Now it is n squared. It's represented just like going upwards. So here, this refers to an algorithm that takes time that is proportional to the square of the input size. Suppose if there are 5 elements and if the runtime is going to be 25, then it is going to be n squared. So a simple example I can say is, I will try to explain in terms of simple examples only, so that this is a very big topic and we'll try to understand how it is represented. So for example, like just take the same example, like we have 5 elements in an array and we are trying to find the product of smallest product of two numbers in that array. So first we can have a for loop iterating each and every element. And inside that for loop, we can have a nested loop checking the product, checking suppose if it's going to be, the first for loop is going to run for 0 to 4 times, and second for loop will run internally again from the first element to the fourth element, so on. So for each element, there will be another for loop running, and that might take the worst case scenario. So big O, as I said, it'll always compare it with, always we will have to denote it with worst case scenario, not the best case one. The worst case, it might take 25 iterations to find out the smallest product of two elements in an array. So this big O notation is represented using O of n square. Another example of n square is like finding the closest pair of points. So think that they have given a list of n points in a plane representing x and y. We will have to find the pair that is very much closest to each other. You can see here there is a for loop running for O of n times, running for 1 to n elements. So this for loop alone will go for O of n. And the inside for loop, again, the worst case, it will go for O of n. So it will be O of n into n, and obviously it is O of n squared to find the closest point, to find the pair that is closest to each other. Okay, logarithmic time. So this is very much useful knowing this time complexity in coding interviews. Obviously, we'll be using it for a lot and lot of problems, especially for searching algorithms. So in this scenario, what happens is if there are n elements, we are going to consider only a subset of the input. So that like if there are n elements, we'll be considering only half of the elements to find what exactly the answer is for a given problem. So in that case, it is represented as log of n. So runtime complexity is O of log of n. So, so find a number in a sorted array. Finding a number in an array, that too in a sorted array, can be done like checking each and every number, but obviously it is going to take O of n time complexity. But since they have given a clue that the array is already sorted, we can make use of this logarithmic time complexity. So since the array is already sorted, we can determine what the middle value is and check if that middle value is greater than that of the given element, whatever element we are supposed to be searching. Then we can just like that omit the lower part or the higher part based on the condition. So that's the that's the searching algorithm. That's what binary search does. Just like that, it omits the other half. So the elements are, so it works for elements which are sorted in ascending order from smallest to greatest. So if you're going to find some particular element, just find the middle value, and then if the middle value is going to be uh, higher than that of the given element, omit higher or the lower side accordingly, and do this iterations again and again to find if a element is present in a sorted array or not. So the brute force, obviously the brute force of this particular approach will be O of n, but the efficient approach will be O of log n. So during coding interview, they will expect us to do the efficient one rather than doing the brute force. So we can explain about the brute force, uh, but then we will have to code only the efficient algorithm. Okay, we saw about linear time, we saw about logarithmic time, and this is log linear. So linear is represented using as O of n, and logarithmic time is represented as O of log n, and the product of both, that is n log n, will be a log linear time. So the very best example for log linear time is merge sort. So there are different so like insertion sort, merge sort, quick sort, and so on. Merge sort is a very efficient sorting algorithm that takes time complexity of O of n log n. So we'll see how it does that operation. So this is a code snippet of merge sort as I was able to take. And for example, here in this array, it consists of 7 elements. So what merge sort does is, the base case is if there is one element in the array, or if there are no elements in the array, then that is the base case. It means the array is sorted. So here there are 7 elements. It will take the midpoint, divide the array into 2 based on the midpoint, and keep on dividing the array into 2 halves until it reaches a single element or there are no elements in the array at all. So this portion here, this portion is the stopping point where it stops to divide. That function is, that recursive call is being stopped, and then it will start merging. It will start calling the merging function. So here it will check for, after it divides everything. So this is, it will compare 27 and 38. It will take it into one single array, and again it will repeat the same kind of operation for all the input elements and tries to merge, and then it has this final output. Okay, and here before merging, until this red point, you can see this is 0 level, first level, second level, third level. Okay, there are 3 levels. So based on this, when we say log n, we always consider log to the base 2. So there are 3 levels. So here there are 7 elements. If it is going to be 7 elements or 8 elements, it will be up to, it will divide, it will go down dividing, splitting the array into 3 levels. That will be for up to 8 elements. So log 8 to the base 2 is equal to 3, and that's how log n comes into picture. So this log n is set in generic level, but when we take 8 elements and do it as log base 2, the answer will be 3, right? And here, if you see the leaf nodes here, all I'm talking about is before merging. So before merging, if you see the leaf, it is going to be the number of elements which are present in the original array itself. So here it is 1, 2, 3, 4, 5, 6, 7. So it is equal to n. So 7, in this scenario, there are 7 elements. So in a scenario where there are n number of elements, the number of leaf nodes will be n. And for each and every level, we will have to do the operation. So it is O of n log n. Okay, we saw about quadratic time, that is n squared. The next level to n square is n cube. So this cubic time is represented using O of n cube. So very simple example is, if there are given, if there are, if they have given, sorry, if they have given an array of n distinct integers, we have to find 3 numbers that sum to 3. You can see the code snippet. We have got 3 loops, nested loops, um, and each loop runs for n number of times. So people like think just if there is a for loop, then we can represent just like that, like O of n. So each for loop it goes for O of n. It is not like that. So for example, you take in this scenario, for this case, for this that summing to 0, this example, here there are 3 for loops, and obviously it is O of n cube. I'm trying to explain, like, think of a scenario. This inner for loop is not going to run for n times, but instead it is going to run just for 10 times. So in that case, the inner for loop will become O of 1, but the outer for loop, if it is going to be n, then it is O of n. So on the whole, it will be O of n. So we will have, on a case by case basis, we will have to check how many iterations does this algorithm contain, and we will have to determine the time complexity accordingly, and not based on just the presence of, not based on just the presence of loops and so on. Okay, we saw from uh, efficient to the least efficient. This is the exponential time. This is going to be a very, very least efficient, I would say, the worst case. There are some problems where, like, kind of backtracking problems and so on, we don't have any other option. In that case, it has to run for exponential time, and there are algorithms that we have to write algorithms which runs for exponential time. A very common problem is Fibonacci series. So Fibonacci series, if you take, for example, if we are going to find the value of Fibonacci of 5, then we will have to know the value for 3 and 4. And for 4, we have to know the value of, you can see the recursive tree here. So for 4, we will have to know the value of 2 and 3 and so on. So here, this repetition, you can see the repetition here. This 3 value will be calculated again here and even here. So this is just for number 5. What happens in case if we take for number 100 or number thousands? You can just imagine how the recursive tree will grow as the input size increases. So this, it increases exponentially, and it is represented using O of 2 to the power n. So here in this case, each and every level, this is level 0, uh, and here it is level 1, and here it is level 2. And a particular level is full if there are 2 to the power I nodes. So here this is level 0, right? So this is level 1. If the for the level 1, if there are 2 nodes, then this specific level is denoted as full. And here's for level 2, 2 to the power 2. So it has 4 nodes, so it is full again. And similarly here for the, this is level 3, this is not full. Okay, only until level 2 is full. And based on the calculation, it takes, sorry, it takes about 2 to the power n by 2 minus 1. So uh, finally it takes like 2 to the power n. So Fibonacci series, when we are calculating using brute force, it's going to take exponential time complexity. So there are different we can make it efficient using dynamic programming and recursion. That's not the part of this presentation. This is just for big O notation. So apart from this, we have factorial time complexity as well. So that is the very, very least time complexity. It deals with, for example, if you say, if you're going to find out permutations of all the numbers in a list and so on, that at the very worst case, it can take n factorial time to run. So that is represented using O of n factorial. So these are the various time complexities. So in case of time, here in case of big O, like for example, if you have a code which has 2 nested for loops and then another, a single for loop and so on, because of the 2 nested for loops that's going to run for n number of times, it will take n square, O of n square. And a single for loop, it's going to take O of n because it's going to run. So we'll be representing it using n squared plus n. And always the it is property of big or like time complexity that we will have to take only the higher dimension one. So the overall complexity is based on the higher power, whichever has got the higher power, and we'll represent O of n squared plus n can be represented as O of n squared itself. And if there are any constants before n square, like for example, it's running for, okay, there are 2 for loops, nested for loops, which are running for like n times, but above that, there is another while loop. It's just running for 3 times. Then it will become 3n square, right? But we will have to drop out the constants and just represent as a whole and tell it as O of n square. We can be very specific and tell it as O of 3n square, but it's okay to say it as O of n square alone. So we spoke about the different time complexities, and similar to that, we have space complexities. So how much memory your solution is going to occupy in. Each and every variable declaration or initialization will occupy some space of memory, right? So space complexity is a generalized measure of total working memory it takes to run a specific algorithm. So if you're declaring I is equal to 0, that specific I will go into memory and take a specific storage. So it has got a constant storage. If it is going to be j or I, it's just that specific location in memory is going to get occupied, and it's not that memory location is not going to increase whatever, we are not going to increase the size of I, right? It's just a specific number we are declaring to I. So if you're going to change it to 5, I is equal to 5, then that specific memory location will be occupied by 5 instead of the 0 that you gave previously. So that is called constant space. Similar to constant time complexity, constant space is O of 1. And suppose you are another example for linear space complexity. If you are trying to copy an array to another array, or better example, I can say, like if you are going to merge two array into a new array, this new array we will have to declare, right? This new array can take the size of both the input arrays. So we will have to declare a new array of size of both the input arrays. For example, if I say first array is of size A and second array is of size B, where A and B are some constants. And this third array, since we are merging the two arrays, we will have to declare A plus B. The size of the final result array should be A plus B. So this, it has to, this new array will occupy this A plus B, that is, which is uh, which is linear, right? Because it, in case if the A changes, the size of this memory location also changes. We will have to expand it, like it occupies such space in memory. That is linear space complexity. Similar to logarithmic time complexity, logarithmic space complexity, like only if there are n elements, if we need only a part of always if we need only part of n element space in memory, then we'll represent the space complexity as O of log n. So log, linear space, exponential space, factorial space, everything instead of time, we are going to consider how much memory it's going to occupy. That's the difference between time complexity and space complexity. But representation wise, both are going to be the same. So this is all about the basic concepts of Big-O. And here you can see the lower the curve is, we have written a very efficient algorithm. The more you go towards the y-axis, it's kind of least efficient. And always during interviews, we will have to have a thought process that gives a solution that has O of n or O of log n to be efficient. And in case if it is constant, it's more good, so on. So any questions? You can feel free to ask any questions.
Hey, Karthika, we have someone in the chat asking if O of n squared is frowned upon for interviews.
Sorry, 1 second. Let me on the chat. What's the question again? Can you please repeat?
Yeah, is O of n squared runtime complexity frowned upon for interviews?
O of n squared?
Yeah, is it like bad to use a solution that's O of n squared in an interview?
If O of n squared is going to be the brute force is something, as I told you, if it's going to be, if you can do a solution for a given problem, if you can derive at a solution, okay, just as I told, for example, uh, searching an element in an array, you can do it in O of n, and you in a sorted array, you can do it in O of n, and you can do it even in log of n, but the brute force will be O of n. In such case, if you're going for the brute force, then it is not an efficient solution, right? So similarly, if the problem statement, the brute force itself is going to be n squared, then they wouldn't prefer that. If there's a better solution than that, they would prefer the better solution. But it's not a case scenario that you don't have to say, like if you don't know the efficient solution, it is not necessary that like we'll just abruptly stop or don't answer anything. We can start with the brute force and then gradually improve the algorithm based on the time. So any other questions? Did I answer that? Unless and until it is not a brute force, it's good to go. If the particular problem statement can be solved in exponential time as brute force solution, but you are going to give a n squared solution, obviously it is better than exponential time, right? So it is good to go. Any other questions? I'll stop sharing my screen so that I can see the questions.
Hi, I had a question.
Mhm.
So in interviews, sometimes you have to write the algorithm quite quickly, and it's just more easier to increase the space complexity by, like copying an entire array into another array, so that you can uh, compute stuff faster. So is that like acceptable? Because you might optimize the time complexity, but the space complexity does increase. So how is it that, like, how do you weigh between the two?
Okay. Okay, you could have seen lead code problems, though the problem statement uh, will be very easy if we are using some additional array or additional list in an algorithm. It will be very easy to solve. But
Mm.
they will be specifying that don't use that additional space. You will have to solve it without using that additional space.
Yeah.
So in such case, we will have to use our thought process by practicing. It's just by practice you will get used to it, you know. So some interviewers obviously expect such kind of solution. It depends on the interviewer, but giving a solution to a problem is far better than not giving anything at all. So always we should try to remember, like, fine, giving an efficient solution should be our aim on the whole. But if you're not able to approach a problem to give a efficient solution, it is okay to give a working solution. You understand?
Okay.
Yeah.
Got it. Okay. Thank you.
No issues.
There's one more in the chat about
Okay.
complexity for a graph.
Okay, for a graph, it is always they have given in a two-dimensional matrix, right? So it is rows and columns. So I wanted to make a slide on that, but I forgot. Sorry. So it is rows and columns. So uh, you take, like, if there are 5 rows and there are 4 columns, and if you are going to check each and every element of the row and each column in that row, then it will run for 5 loops for that specific row, and again 4 for each column. So it will be 5 into 4, that is 20 times we will have to run if it is going to be a two-dimensional array, that is a matrix, right? So similar to the question that is graph, it is m into n. So where n is the number of rows and n will be the number of columns. And if we are going to have two nested for loops as quadratic equation, time complexity, we mentioned that we can represent it as O of n squared. But what if there are different number, like the dimensions of the rows is different from the dimensions of the column? Then we will have to go for m into n, so on. So it depends on number of rows and columns. So here it is uh, here vertex plus edges in graphs, right? So we will have to for graph kind of problems, we'll be focusing more on we'll be having a hash map traveling through each and every vertex and the connection to those vertex to other vertex, so passing through each edge. So in that scenarios, it will be vertex plus the edges we will have to cover. So the two statements that I gave, it's one for matrix, another for graph. It will be covering both vertex and edges. So we will have to represent as O of vertex plus edges that we are covering. So though we are not in a graph, if you're not think that it is a disconnected graph, there are various components, and if we are not going for all the components, only for specific, though it is going to cover only specific vertex and edges, the worst case scenario, we will have to cover both the components and we will have to represent it as O of vertex plus edge. Did I answer the question?
Yes, thank you.
Measures. Any other questions?
Yeah, Isabel has one. When solving problems, are there common strategies that you use to reduce runtime?
Yeah, as I told you earlier, the more and more problems you solve in lead code, the more and more strategies you will know, you'll come to know like how to handle problems in order to reduce the runtime. There are like specific 75 questions in lead code that you'll have to, that I feel it will get make you adapted to various topics like trees, graphs, and so on, and very like dynamic programming, backtracking. And the more and more you practice, you will know, you'll come to know how I can, like for example, this sorted one, the moment you see it is a sorted array, your mind will start thinking, oh fine, it is sorted, I should not do it in linear time, I can do it in a binary search and do it in a more efficient way. So it's based on practice, and the strategies that you come to know is just based on practice.
I'm gonna stop the recording.